We'll continue talking about base shrinkage and um, just to summarize the previous example, the example of the schools. So we have 8 schools and um, we wanted to estimate a treatment effect, and we measured treatment effect by the results of the SAT exams. And we had 2 different strategies. So the actually 3 different strategies. The first strategy is to estimate the treatment effect for each school separately. And what we saw, this is unbiased estimation, so that's unbiased, but it is of high variance. If you saw the variance, BLS for each of those schools, there were large deviations, so there's a large sampling error for each of those schools. And the second way was pooling. And if you remember, the pooling was low variance estimation, but it was biased because we essentially, if we want to, so if you think from the about this problem from the standpoint of prediction, when you try to predict how well each of those schools will do under those different treatment policies in the next year, so you try to predict the next year SAT outcomes, then if you use the pooled estimator, so every school will do the same way, and so it's a low variance estimator, but very biased, of course. And if you do the separate, so you have unbiased estimation for each of schools, so each school will have its own little prediction, but it's of high variance. So you have to, there is high uncertainty associated with this prediction. And essentially, the hierarchical model allows us to do this shrinkage. Essentially, shrinkage allows us to find something in between this completely separate and complete pooling. And we have this parameter tau that controls. And essentially, you can think of tau to control this bias variance trade-off. Again, if you think from this problem about this problem in the context of predictions. And we're going to see a couple more examples of Bayesian shrinkage. We're going to see the baseball betting average, and we talked about the Stein's paradox. Um, and we're going to look at Bayesian elections and portfolio selection. So we will apply this Bayesian analysis to analyze performance of bettors, and we'll look at this better pitcher matchup. And we're gonna assume some prior on ability of a player, and we have a small sample size, and there is variation from pitcher to pitcher. And let's look at Jeter. Jeter was a famous bettor from New York, and let's call P to be his true betting average, or his true ability to hit successfully. So this is the true and unknown ability. And we have an observation, so we have a number of successful hits, yi, for him, so that's our data. And the likelihood is binomial, so the outcome of each at bet is either successful or not successful. So the number of successful outcomes given the true betting ability is binomial distribution, and Ti is the number of attempts made in the given period when the observation was made, and the Pi is the success of each at bet to be successful. And to get the conjugacy, we're going to assume the beta pi distribution over this parameter pi. And we're going to choose alpha and beta in such a way that the expected value of pi, you remember expected value of the beta distribution is just alpha divided by alpha plus beta, and we're going to choose them in such a way that they just equal to pi hat, so that's the average number, so that's yi divided by ti. The average number of successful bets for Jeter. And you remember the variance for the binomial for the beta distribution. Now we can just write it in terms of pi hat. It's just pi hat times 1 minus pi hat times this additional term, multiplicative term phi, which is just alpha plus beta power minus 1. Let's look at another application of it. We'll look at the Kenny Lofton example. Kenny Lofton was a batter, and here are his outcomes for hitting against different pitchers. So this is the list of pitchers. And for each pitchers, you have the number at bats. So how many times Kenny Lofton came at bat against this pitcher. So that's the TI. And then you have hits. So how many successful hits he had. So that's your YI. And then you have your observed average. So that's your YI bar, which is just the number of attempts divided by the number of successful hits. And Kenny Lofton, his career average was 2.99, so he's roughly 300 hitter. And in 2006, his average was 306. So looks like 2006 was a slightly better year for him. And he was facing the pitcher Milton, and his current record is 1 for 19. So let's go back and find Milton. So you see when he goes against Milton, his betting average is very low, slightly above 5%. And what happened, he was rested and replaced by 2.75 hitter. And the question was, is putting a weaker player really a better bet? And if you calculate the probability of this record, 1 for 19 using just binomial model, you get 0.01. So this is very unlikely to happen by chance. So we're gonna do the Bayesian solution. We're gonna calculate the shrinkage estimation for his durability to bet, and we're gonna use the posterior mean. And for him, his betting average was from 2.65 to 3.0, the lowest betting against Milton again. And so what happens is all of the betting averages basically got shrunk. And if you look at his lower end of the distribution, it's of this interval, it's 2.65, so it's actually below 2.75. So from the Bayesian perspective, replacing Milton with a person who is 275 hitter was justified, because on the left end of the ability scale, Lofton was 265 better. So the conclusion from this analysis that resting Lofton against Milton was a well justified thing. Okay, so we're gonna go back to Jeter, and again we're gonna consider this Bayesian model, beta binomial. Yi is the number of successful outcomes, P is the true betting capability of the player, Ti is the number at bats, and we're using conjugate prior, the beta prior, and Ti is the number of at bats against each pitcher, and we're going to estimate parameters alpha and beta. And this is the same data set for Jeter. So you have all of the pitchers here, and you have your TIs, you have your YIs, and then you have here TI divided by YI, and then you have estimated average. So this is just the shrunk average that comes for this specific pitcher, and then we have 95% interval for that estimation. So this 3.22 is in the middle of this interval. And the phenomena you see here as a result of this shrinkage estimation is that all of them got shrunk towards the total average. So towards global average or pooled average. Pooled average. Okay, so remember in that year his average was 308, and you see all of the individual estimation would vary around this number. And so Mendoza seems like he has a very great record against Mendoza, but our Bayesian model says that his true capability to bet against Mendoza is 3-2, not 8-3, what we calculated by just taking 5/6. So what it means that if we are to do a prediction for the next year, how Jera is gonna do against Mendoza, our prediction is gonna be 3.22, and this prediction based on the fact on his performance against other pitchers. And the intuition behind that is that maybe it was just an outlier, maybe just his performance of 8.33 against Mendoza was not a typical thing. Why would it be so different from any other pitcher? And we just corrected it with Bayesian shrinkage estimation. And for the prediction, we should use this corrected or biased estimation of betting average. It's biased, but lower variance, you remember. Okay. Um, so, and this multiplicative term for the variance, alpha plus beta plus 1, is just 0.02 for Jeter. So it doesn't vary much across the population of pitches. He is very consistent. And the extremes are shrunk. The most also match up with the smallest sample sizes. So the smaller the sample size, the more shrinkage you get, which makes sense. So the sample that comes from the small number observations gets less weight. Again, his average for the season was 308, and the base estimate varied from 311 from 327. So he's very consistent. And if all players had a similar record, then a constant betting average would make sense.